It's good to come your way once again. In our previous lesson, we have looked at how we can perform basic operations on rational functions and realize that performing basic operations on rational functions is just like when we perform operations on fractions, right? So when we add fractions, when we subtract fractions, we see that first we must find the LCM and then go through the process of simplifying the rational functions so that when they are in two forms, we can make it one. My name is Nana Yawedu, and you can call me Say Nana. Remember to like this video, share this video, subscribe to my YouTube channel, and don't forget to click on the notification bell so that you can get all videos on time. In this lesson, we want to consider how we can decompose rational functions. We want to look at how we can separate rational functions so that we can use that in performing various functions that will help us make things simpler for us. So what does it mean when we are decomposing rational functions? Now, let's consider this. Basically, when we have plane shapes like the rectangle, right, for instance, we can get the area of the rectangle simply by multiplying the length times the breadth, right? So the area of a rectangle is length times breadth. But then with the rational functions, we know that the graph of the function can be a curve, right? So anything in the area of a curve, right, will be the graph of a rational function. So probably a rational function f of x, which is equal to g of x all over h of x, right? So in dealing with rational functions, sometimes we must be able to find the area around the curve. And this involves the use of basic calculus techniques, right, such as integration, right, where we find the minute areas of each of the areas, and then we are able to find it under the bounds that have been given. Now, to be able to do this, sometimes the rational functions given to us, it is difficult for us to perform the basic operations of calculus, right, like integration. So decomposition into partial fractions, right, is a technique used to simplify and decompose rational functions into sum of simpler fractions, right? So we want to separate them into sum of simpler fractions so that we can use them when we are dealing with complex rational functions or when we want to work on integration and differentiation, right? Which is basic calculus, or solving equations in a more manageable way. So that is why we engage in decomposition into rational functions. And when we are decomposing rational functions, we consider the type or we consider the denominator or how the expression of the denominator looks like, right? So we say that when we have an expression, right, where the denominator has linear factors, right, linear factors that are not repeated. So for instance, s minus p, s plus q, s minus r, we express them as a over one factor plus b over another factor plus c over another factor. So for instance, if you have 5 all over x minus 1, right, s plus 2, these are linear factors. They are linear factors because their expressions, right, x minus 1 is equal to 0 can be written as x is equal to 1. And this is a linear factor, right? Or x plus 2 is equal to 0 can be written as x is equal to negative 2. And this is also a linear factor. So these are linear factors. So you always check the denominator parts of the equation. Once you see that they are linear factors, right, with different factors, we can express them as a over one factor, s minus 1, plus b over another factor, s plus 2, right? So rational expressions with linear factors as denominators can be decomposed, right, as follows. So you can write the expression and write it as a over one factor plus b over another factor plus c over the other factor. So now let's consider how we can solve decomposition with linear factors. Let's consider this example. So the example says that resolve 3x plus 2 all over s plus 3 s plus 2 into partial fractions. So let's look at how we can resolve this into partial fractions. So to be able to resolve this into partial fractions, the steps is to first write out the decomposition. So what has been given to us is 3x plus 2 all over x plus 3, right, s plus 2. And we want to consider the denominator. Realize that The denominator are linear factors, so we want to write them in the decomposed form, which is a all over x plus 3, right, plus b all over x plus 2. And then what we do next is that we want to decompose, right, and find a and b so that we can write it in that form. So we would consider the right hand side of the equation, because for the left hand side we can't do anything about it. So we'll write the left hand side 3x plus 2 all over x plus 3, right, x plus 2. So this is equal to the right hand side. We want to find the LCM, right? So finding the LCM, we have x plus 3 and then s plus 2. So s plus 3 goes into s plus 3, so we have a multiplying the expression s plus 2, right? Then we have plus s plus 2 goes into s plus 2, so b multiplying the expression s plus 3. Now we see that the denominators are the same, so we can say that since the denominators are the same, right, we equate the numerator. So we equate the expressions in the numerator, or the numerator parts of the expressions. So we equate the numerator. So that implies that we are going to have 3x plus 2 to be equal to a multiplying x plus 2 plus b multiplying x plus 3. Right, so once we get here, what we are going to do is that one way of solving this, so from this side, we can consider one method from this side. So one method of solving this is that we can take the factors one by one. So we will take x plus 2 and equate to 0, and then get x to be equal to negative 2. And then we substitute x is equal to negative 2 in place of x in the equation. So that implies that we are going to have, right, the expression 3 multiplying negative 2 plus 2 to be equal to a, right, we have negative 2 plus 2 plus b, right, negative 2 plus 3. So we see that the a part of the equation goes to 0. Then we are going to have 3 multiplying negative 2 to be negative 6 plus 2 is equal to, right, the a part goes to 0. So we have b, right, negative 2 plus 3 gives us b. So it means that we are going to have negative 4 is equal to b. So we get the b part of the question. And then now we will take the other factor, which is s plus 3. So s plus 3 is equal to 0. So x is equal to negative 3. And then once we get that, we are going to substitute negative 3 in place of x in the equation here again. So you are going to have 3 multiplying negative 3 plus 2 is equal to a, right, negative 3 plus 2 plus b negative 3 plus 3. So we see that the b goes away in this case, right? And then we are going to have negative 3 multiplying 3 gives us negative 9 plus 2, right? And that is equal to, we'll get negative a. So we get negative 7 is equal to negative a, right? And then we see that we can divide through by negative 1 by negative 1. So that we are going to have a to be equal to 7. So we'll rewrite, and then we'll move, right, the a and the b in place of what is there. So therefore, our decomposed form 3x plus 2 all over s plus 3, right, s plus 2 is going to be equal to the a is 7 all over s plus 3, right? And then we have minus, because the b is minus 4, so minus 4 all over s plus 2. So we have decomposed 3s plus 2 all over s plus 3, s plus 2 to be equal to 7 all over s plus 3, right? And then minus 4 all over x plus 2. So that is one way of solving for a and b and simplifying a partial fraction. Now let's consider an alternative method to solving this. So alternatively, once we have our 3x plus 2 all over s plus 3, right? X plus 2, and we write it in the form a over s plus 3 plus b all over s plus 2, right? We rewrite 3x plus 2 all over s plus 3, right? S plus 2, then that is equal to, we find the LCM, s plus 3, then s plus 2, then we have a multiplying s plus 2, right? Plus b multiplying s plus 3. So plus b multiplying s plus 3, right? We know that the denominators are the same, right? So we say that since the denominators are the same, then it means that 3x plus 2 will be equal to a multiplying s plus 2 plus b multiplying x plus 3, right? So this process is the same for the other method. Now we want to look at the alternate method, so a second method. So you can use any of them when you are solving for these questions. So what we need to do is that we'll take the left hand side, which is 3x plus 2, and then on the right hand side we expand. So we get a multiplying x plus 2a plus b multiplying x plus 3b. Then we group like terms. We pick all the ones with x to one side and then all the constants to another side. So you are going to have 3x plus 2 is equal to ax plus bx plus 2a plus 3b. Then we compare. So comparing the coefficients. So comparing coefficients. What it means by comparing coefficients is that what we are going to do is that we are going to compare the x term on the left hand side with the x terms on the right hand side. Then we equate them. So it means that we are going to have 3, which has the x term right here, to be equal to a plus b. So we call it one equation. So this a has x term, b has x term. And then we take the constant 2, and then we compare it to the constant here. 3a is a constant, 3b is a constant, because a and b gives us a constant value. So it's equal to 2a plus 3b. That's equation 2. So we see that we get a simultaneous equation involving two variables. So we can say that a is equal to 3 minus b. We can call it equation 3. And then we put equation 3 into equation 2. So we are using the substitution method, right? So we have made a the subject in equation 1. So we move b across the equal sign. A is equal to 3 minus b. We call it equation 3. Then we put equation 3 into equation 2. So we get 2 is equal to 2. Wherever we see a, we put what? 3 minus b there, plus 3b. Right, so you have 2 to be equal to 2 multiplying 3 gives us 6 minus 3b, right? So minus 2b instead. So 2 multiplying 3 will give us minus 2b, right? Then plus 3b. So this implies that you are going to have 2 is equal to 6 plus b. So our b is equal to 2 minus 6. And then our b is equal to negative 4, right? So we get the same value of b, which is equal to negative 4. And then once we've done this, we want to go through and get our a as well. So we are going to substitute b into equation 1, right? So put b, which is equal to negative 4, into equation 1. So that implies that we are going to have 3 to be equal to a minus 4. So when we move a across the equal sign, we will have a to be equal to 7, right? So therefore we can write our expression, right, as 3x, right, plus 2 all over s plus 3, right, all over s plus 3, right, as one factor, and x plus 2 as another factor, to be equal to, right, a is 7, so 7 all over s plus 3, then minus 4 all over x plus 2. So we have resolved into partial fraction as 3x plus 2 all over x plus 3, x plus 2 to be equal to 7 all over x plus 3 minus 4 all over x plus 2. And this is a form that we can work with easier, right? So we've simplified it or decomposed it into forms that we can work with easier. So in this lesson, we've looked at how we can solve for partial fractions where we have linear factors. We've used two alternate methods to be able to solve this. In our next lesson, we want to consider another question on solving for partial fractions when we have linear factors. Remember to like this video, share this video, and subscribe to my YouTube channel. See you in the next lesson.